In this video, we present motion control of high-dimensional musculoskeletal systems with hierarchical model-based planning. Our target problem is the control of high-dimensional musculoskeletal systems. It has high-dimensional state and control space and high nonlinear system dynamics. For example, the human full-body musculoskeletal model we used in this work has 90 rigid body segments, 206 joints, and 700 muscle-tendon units. Currently, the predominant methodology for high-dimensional musculoskeletal control is deep reinforcement learning, but it requires long training time for effective control, typically hours to days. It also demonstrates poor generalization to different environment or model states. Here we show some failure cases of DRL agent trained on flat ground. It fails when the terrain condition changes, and fails when the posterior leg muscles are suddenly disabled. Our goal is to develop a method to control high-dimensional musculoskeletal systems with following properties: near real-time control generation, training-free deployment over different tasks and environments, robust performance subject to sudden model changes. Our idea is using sampling-based model predictive control instead of DRL, because MPC satisfies the above desiderata in many control problems, and the sampling-based control optimization procedure can circumvent the high-dimensional state issue. However, sampling-based MPC cannot effectively sample high-dimensional controls, and we need to address this problem to control the musculoskeletal system. We propose model predictive control with morphology-aware proportional control, aka MPC square. It uses model predictive position controller to plan the target posture of the agent, and use instant rollouts for rapid response to state changes. With the high-level target, MPC square uses morphology-aware proportional controller to coordinate actuators to target posture based on inverse dynamics. We use actuator Jacobian to set proportional gains because it transfers actuator forces to joint torques. In this way, we can reduce high-dimensional optimization burden of gain design and prioritize major actuators for movement based on system morphology. Using actuator Jacobian, we can successfully identify major muscles during human walking. We first evaluate MPC square in standing and walking task over flat floor. Our method can achieve near real-time stable control of the full-body musculoskeletal model. The successful full-body motion control does not need reference trajectory. Compare with state-of-the-art deep reinforcement learning-based method, MPC square can achieve training-free deployment and has better energy efficiency. MPC square can also complete navigation tasks over different environments, demonstrating zero-shot adaptation to different tasks and terrain conditions, such as walking over rough terrain, walking up and down slopes, and walking up and down stairs. Our method demonstrates generalization to changes of model states. It can achieve adaptive walking control under sudden actuator failure, for example the posterior leg muscles injury. It can also generalize to random perturbations, demonstrating rapid response to sudden perturbation forces to the pelvis. MPC square can also generalize over different embodiments. It can achieve stable control over ostrich musculoskeletal system using same controller and cost function as human walking, and complete dexterous manipulation task over arm musculoskeletal system. The fast control generation of MPC square can facilitate efficient cost function evaluation. Combined with Bayesian optimization, we can achieve automatic cost function design, reducing the need for human-intensive reward engineering. In this way, our method enables control of agile sports imitation, such as soccer movement. In this paper, we propose model predictive control with morphology-aware proportional control. It is the first training-free method for high-dimensional musculoskeletal system that can achieve zero-shot near real-time high-dimensional control, demonstrates generalization over different task, environment, perturbations, and embodiments. It can also facilitate automatic cost function design when combined with Bayesian optimization, reducing the burden of human reward engineering. Thank you for watching.